One way to talk about reactive applications is to look at the execution model and the way that we scale applications. If we had a time machine and go back 20 years to the beginning of the internet, Java was also just born. At the time, CGI was a common way to process requests. Imagine that, a new process for every incoming request. Of course, today that's unimaginable, but it was in this context that the servlet API was born and servlet containers came to introduce a processing model where we take advantage of the multi-threading capability of the JVM. And the basic contract would be that each servlet, the servlet container has a thread pool, assigns a thread for each incoming request, and you can process that independently of other requests. A simple model that you can use to build applications that scaled pretty well and that's taken us pretty far. And we still use this model today. So let's take a closer look at how this works. So we have a container, servlet container with a thread pool, and that thread pool is going to process incoming requests. And of course, we're sensitive to the latency of incoming requests. And if we have more slow clients, for example, we have to allocate a bigger thread pool, and that's the kind of game that we need to play. Of course, at the same time, the application itself has latency. So you can imagine, for example, you can decide to use application-level thread pools to make requests as well. And as you do that, you also have additional network latency. And eventually, when you have too many requests at peak loads, eventually you will reach out-of-memory exceptions. So then what we do is we try to scale horizontally. We add a load balancer, and we have multiple servers. When we reach the limits of a single JVM, we scale in this way. And as we do that, the load balancer may ask, are you dead? Are you dead? And if there's no reply, then we take out that server. And this model has taken us pretty far. In fact, arguably, there probably wouldn't be so much to change. There wouldn't be a very strong reason to make changes if things had remained the same. But of course, over the last 10 years, things have changed dramatically in the way we develop applications. Just in the same way that, for example, Google Maps changed expectations about how interactive web applications can be, and we moved from very static HTML pages to AJAX and interactive web applications. In the same way, the rise of social media becoming mainstream, I would argue that it set our expectations in very subtle ways about the interconnectedness and the scale of applications. So today, we pretty much expect that our applications will have similar characteristics, and we try to emulate a lot of that. We also deploy applications in the cloud. We build microservices and distributed applications. These are things that become normal. Maybe not everybody develops applications like that. But certainly, this is something that we know and aspire to, and something that is important, and that is the way that we look forward to develop applications. So let's also take a look at how we actually scale in the cloud.
So today, and probably yesterday, you've seen a lot of this presentation embracing the concept of elastic scaling. And with microservices, the dream is if you want to deploy or need more resources to keep going on peak load, for instance, you can just have the auto-scaling capability for you deploying new instances of your application. So for instance, B is under peak load, you can deploy more application B, and you make use of your mutualized resources more efficiently. And that's great. Because the cloud will offer you all these computing resources, and you can even reuse them 2 times, 3 times if you want to. You can undeploy them after the peak load, which is great because you want to save also a bit on money. That doesn't come for free. But Mostly, if we look really what we do today, especially and unfortunately in the JVM world, some applications are developed with an uncontrolled backlog of things to do. And we think about, for instance, the classic server container, where you can accept as many requests as you can, but it's going to take a lot of memory or a lot of resources of your application. So the footprint of your application is necessarily going to be bigger, and you won't be able to utilize the resources as you want it to. So basically, application A here is spanning across the two resources. But the thing is, if you want to really scale out this kind of architecture, you will have to use a new instance, a new hardware, and that's going to aggressively introduce some cost in your architecture. And you will make some people happy, obviously. That's certain, but I'm pretty sure you want to get, especially with platforms such as Cloud Foundry, the most of them and the most efficiently possible. So, yeah, can we do it differently?
So if I don't want to spend any extra money, then is there any alternative?
Well, there is, there is a world where you can meet with new friends, like Rick and Morty here, and this world is about non-blocking runtimes. Non-blocking runtimes, you've heard about them before with Node.js, with Netty on the JVM platform, and such. And they all consist, first, in using the minimum resources possible in your system. So a main characteristic of these runtimes is actually to use a few threads compared to, for instance, a servlet container, which use a lot of thread if you are in a blocking mode, especially. These new runtimes, well, not that new nowadays, these runtimes allow you to actually use these few threads to do great things. And we've seen examples of Netty and Node.js deployments in a lot of environment, very stressful environment. Netty is used, for instance, at Apple for all the iCloud stuff. So it's quite solid for the few threads they try to use. But in dealing with the incoming traffic, you will have traffic coming from slow connections like mobile phone, and some coming from broadband, so high-speed connections. With this kind of approach, at least you have a decoupling with the write and the read capabilities. So you will naturally prioritize the fastest, reward the fastest connection with a response, and put on the backlog the slowest connection. But unlike the servlet container, the slowest connection are not going to affect the fast one. And that's quite good if you want to be available for at least rewarding this fast connection and save a lot more. The problem is, like actually the servlet container slide we just seen before, the problem is if you have this kind of capacities, the problem of blocking at the processing level doesn't go away naturally. Especially in that case, it's going to be worse, much worse, because if you start blocking these famous event loops, as we call them, you actually kill the system much faster actually than the servlet container, because the few threads here are responsible of everything, and yeah, you can't block them. So in that case, we might need to change also the way we develop applications, and we need a way to develop non-blocking application, not blocking application, if we really want to use these new runtimes.
Yeah, in fact, Netty and Node.js are just two examples of non-blocking runtimes first, but Tomcat and Jetty also use a similar model underneath, and if you use the non-blocking I/O, you can achieve similar end results. But the thing which is really important to understand here is that if you have a non-blocking runtime, you're talking about using a very small number of threads, as Stephane just pointed out. And if your application does not embrace asynchronicity and does not embrace a non-blocking mode, then you will not be able to operate because you have very few threads, and if you start blocking those threads, then your entire server is blocked. And probably the easiest way to think about that is about Node.js. There's a natural constraint where you have to use a single thread in order to process everything. So you can imagine that in that kind of constraint, with that kind of constraint in mind, you really have to make everything non-blocking. Asynchronicity cannot be an afterthought. It cannot be something that you throw when you have something that's really slow. Non-blocking is something that you now have to do by default when you have places where you anticipate latency. So that is a big, big, major change. And in order to build such applications, it's actually really not that simple, really not that easy. And I'm sure you've heard it from Node.js and from other places. When you start getting into developing applications like that, there's different words for it, callback hell and others. But here, for example, is the steps to boil rice. Imagine that you have a chef in a restaurant and you want to boil some rice. You want to describe how to do that. Well, you really don't want to wait until the water boils, because then you'll have a lot of hungry customers. You want to basically describe the same algorithm of what should happen, but you don't want to do it in this way, where you say, OK, add some water. Now, when this is done, lower the heat, and then add the rice, and then give it a little bit of time. What you really want to do is you want to declare the same algorithm. We're going from imperative to reactive, so instead of specifying steps one by one and blocking potentially, what we want to do is we want to lay out the algorithm declaratively instead of deal with these kinds of callbacks. So in order to deal with callbacks and asynchronous programming, in order to achieve a kind of Zen, we really need to rise above the callbacks, and we need a declarative API to do that. So let's take a look. What do we have actually in Java that's available for that? Well, in Java 8, we have the completion stage, which fundamentally is the right idea for an asynchronous API, because it gives you primitives that you can use to declare logic that should happen after the feature completes. Things like when, complete, and then you provide a lambda expression. So you're not going down a nested callback hell, but you're declaring the logic and you're composing that logic. But completion stage and completable feature are not really perfect for this because they don't really deal with what happens when you have more than one value. If you have collections or latency-sensitive data, which is very common in non-blocking applications, there's really no answer for that. Well, we do have the Java util stream API, and that's another example of the kind of declarative composition API that we want. It provides operators. It operates on streams of data, collections. But that's really why we can't use it either for our purposes here, because the stream is really built for collections. It doesn't really deal with latency-sensitive data, infinite streams, any of those things that actually arise quite commonly. And don't take this from me. These are not just my words. This is what Doug Lee had to say when he introduced adding the reactive streams specification, incorporating the reactive stream specification into Java 9. And he basically indicated that the Java util concurrency module in Java doesn't really have an async API to fit exactly what we're talking about here, which is the ability to push data from a hot source as it becomes available. That's latency sensitive, that's potentially infinite streams. We're not talking collections here. So that is what we really need. And this is why we have Project Reactor that I'll get to in a moment. But just for a second, I want to talk a little bit about what Reactive Streams is. So Reactive Streams is actually a very small, very simple specification that was created through industry collaboration. It's actually an interesting example in itself of a bunch of companies coming together and creating a specification that was useful enough to be included into the JDK, to be just picked up. This specification is available and ready today, and we are using it in the Reactor project and in Spring 5. And it's basically a very simple idea. You have a publisher and a subscriber, nothing new there. The one thing which is different is that you have the concept of back pressure, which you can think of as a volume control that allows the subscriber to indicate to the upstream publisher source whether it's ready to consume more data or not. And if the subscriber or the consumer is not able to do that, then the publisher is not supposed to produce. So you can imagine an entire pipeline of components going all the way from the database to the HTTP socket with the application in the middle, the web framework, etc. And this kind of back pressure being propagated so that if the client is slow, maybe a mobile client, and is not able to consume more data, we can go all the way back to the database and indicate that we're not ready to consume more data. And here we have Project Reactor. That's a major part of the Spring 5 story. And Stephane, as the project lead, is arguably the world's leading expert.
Yeah, it's probably on Project Reactor itself. But the Project Reactor, as we see it today, the story of the Project Reactor, and we are talking about Reactor 3.0, is really a translation of completion stage to Mono as a reactive alternative, and Stream to Flux as also the reactive alternative. So basically meaning we can deal with latency, unlike these two JDK standard components. So the Mono and the Flux are just types. You use them at very low level, actually. They are like future completion stage. You use it directly in your application, and you start developing with them. They are documented as such. We call that kind of diagram, marble diagrams. And pretty much people familiarized with the Arak Java project or the reactive extension will recognize this. Actually, the project Reactor itself is developed in collaboration with the Arak Java lead. So we have a bunch of sharing and concept sharing between them, but we're not entirely married to the concept of reactive extension for those who know them. And the Flux is the same thing, but for end data, so 0 to end data. So you can actually think about streaming back WebSocket events or any kind of SSE or any kind of multiple value return, including even reading from database, for instance, that might have multiple results that might come at different time, depending on the latency again. So where we see it is actually at a very low level. Just to clarify the positioning of Reactor, it's just providing you with these two types, and we're here to help various components, especially in Spring framework and the Spring ecosystem. We help communicating between these various components. And we transmit data. It can be from Spring data. For instance, we can consume data and tell Spring data, maybe you shouldn't retrieve more than these 32 elements, these 32 items. That is kind of thing we can do now. Also, we can think about sending this or receiving this data from HTTP connection, HTTP endpoints via Spring Cloud, for instance, or even through Spring messaging as well, because that's a classic example. But you will see this, actually, these are very different kind of treatment we need to apply, because one of them, Spring data, is going to connect, for instance, to a data store behind. And the particularity of that is the source of this data is somehow replayable. That means if you are very slow, you can pause indefinitely the data source, because you can replay anytime. There is no constraint. So that's quite good. And even if you want to retry, etc., that's also very helpful. And the whole concept of back pressure, in fact, is to leave the data where it is at first to avoid consuming it. If you cannot consume it, because if you wanted to consume this data, you will actually overflow your application, and that's when you start getting blocking, and that's the thing we try to avoid. You have also, if you start communicating with another microservice, like service B in this diagram, you will also have this concept of back pressure as well. You can also say to this service, I'm not ready to read the data yet, because my client itself, the traffic incoming through the gateway, is not ready to accept this data, is not ready to consume this data at first. So end-to-end back pressure. And the challenge as well comes also from hot sources. So hot sources are kind of source of data where it's critical to accept them as fast as you can, because actually you cannot replace them. They are temporary or very temporal data. For instance, think about trade books flowing into a Spring messaging or Spring Cloud Stream architecture. That's the kind of thing you can't pause forever or cannot pause at all, so you will have to actively deal with back pressure in this case. And really, the end-to-end flow control we want to apply by inviting you to use these new types, flux and mono, end-to-end, and invite also, use the new capacities from each of the Spring Framework projects. What we want to make you understand, actually, is to see that this flow end-to-end is working a bit like photon and electrons and proton. If you proton and electron. If you remember the physics course you had in college, for instance, that's the kind of same mechanic that applies in IT in systems. Actually, two systems are going to communicate back pressure. One is going to have a force that's going to attract, that's going to ask for consuming data, but not too much, because if it starts consuming too much, and that's the opposite force, it's going to start blocking. And that's really what it is about, this back pressure thing. So we can do that now, and we started working on that nearly 1 year ago now with Spring Framework 5. And that's actually a great thing, because with all the ecosystem we have in Spring, we cover a lot of use cases, basically, when you create an application. And we can deal with this back pressure under the hood without you even noticing. You just compose your application. You use the new primitive from Flux and Mono. You can transform. You can filter, etc. So that's great. Now it can be directly used through the Spring Framework 5.
So you can see how we went from a mode where we have a thread pool for processing incoming requests, and we need to keep that a large thread pool. But we really have no control boundaries at different places in our application that would ensure that data remains where it is, and to have queues necessary to transfer the data as it becomes requested and possible to move it through. So this is kind of a very different way of thinking and doing things, and it requires very deep change. Now we can take a look more concretely at what we already have with Spring 5 in milestone 1. So when we first started out about 1.5 years ago, we really had no idea what this is going to involve. We just knew that we wanted to go in a direction where you kind of scale differently and use a different threading model, a kind of a non-blocking style of your runtime, and then allow applications to work without blocking. And one of the first things that we began to realize is that the controller programming model, fundamentally, there was nothing blocking or incompatible with this reactive picture that we're painting. The flexible method signatures are perfectly capable of dealing with reactive types, and we can support the same programming model on a completely non-blocking reactive foundation. And as we began to embark on this journey, I mean, 1.5 years ago was probably the early days when Arak Java became 1.0. Reactive Streams wasn't out yet, and those were the early days of Reactor as well, experimenting both with Reactive-X style operators and with Reactive Streams. But soon we began to realize the important role that Reactive Streams has to play, and the concept of back pressure, and also the need for declarative style composition API. And at that point, we knew that Reactor was an important part of the picture, so we began to double down on our efforts, which really meant taking Stephane and duplicating him so that we can have one in regular hours and another one for off hours. We've been working very closely together, trying to build out what we want to do, and then gain insight and experience through collaborating, and also to see what the end results would be. And where we ended up with is we now have a web reactive module, which is parallel as an alternative to the Spring Web MVC module. So it's all about what happens underneath. We need a reactive foundation to support that controller programming model, and this is what we've built. At We have all new contracts that are very similar to the ones in Spring MVC, but they have non-blocking semantics, and they're built on reactive streams and Reactor. And most importantly, they consume the request and response and write to the response using a reactive style API. So you have a flux of data buffers, for example, for the input of the body instead of a servlet input stream and servlet output stream, which means that you can consume and you can write to the HTTP socket with back pressure. And also we have reactive encoders and decoders to do JSON and XML in non-blocking style conversion. So we've done all that work to get there already. And we have built that on top of Tomcat and Jetty, and we can adapt to any Servlet 3.1 container as well. I mentioned Servlet 3.1 not only because it's a base requirement for Spring 5, but also because Servlet 3.1 provides a non-blocking I/O API, which allows us to essentially build a bridge to reactive streams so we can translate back pressure to and from the underlying HTTP socket. But it doesn't really stop there. The advantages of this approach means that we can now support other runtimes, including non-servlet containers. So we run on Netty as well, and also Undertow. Both of these are non-servlet containers, and we can support all of that. And we believe that we have a very unique proposition, value proposition, because if you look at all the existing reactive offerings, they all focus on pretty much a single runtime. Our approach is a bit more inclusive, and it's consistent with the Spring philosophy to provide choice. So you can do Tomcat, you can do Jetty, you can even do any Servlet 3.1 container, or you can do Netty and Undertow, and this is a really great place to be. So I'm going to show a few examples. Again, it may look a little bit underwhelming because ultimately the programming model is very similar. The main thing which is different is what happens underneath, and also the support for reactive types in method signatures, the full support. So in this case, we have an HTTP GET, and we're returning an account. We're using actually a reactive repository. Maybe some of you went to the Spring Data session yesterday to see that this stuff is actually already real, and it's coming very soon. And this account is going to be written out to the socket. We have reactive streams, pipeline here set up all the way from the repository to the HTTP connection. We can do the same thing on the save side, HTTP post. Here we take an account. And this is a really new capability. I mean, maybe this is something that will strike you as being quite different. The notion that we can consume the request body in an asynchronous fashion. That this method will be invoked before we've actually read the body, and that you can declare an operation on what to do after the body has been fully read, without taking any extra threads if the client is slow and without blocking. And then we save that and return a mono void which indicates success or completion in reactive composition style. That's how we communicate the outcome. Again, remember that this is no longer imperative, and I do have a session after this to talk more about that. Certainly from a programming model perspective, it is a change. You know, there's no two ways about that, but hopefully you understand why we're going through all this. Now, we also support Arak Java fully, and again, this is consistent with Spring's philosophy. Arak Java is a first-class citizen if you want to use that in your controllers. And as Stephane mentioned earlier, it goes way beyond simply supporting Arak Java. We actually have very close collaboration between Reactor and Arak Java. And that alignment is actually very important if you're including multiple reactive libraries and you have a single pipeline, which is how it's supposed to be. In general, you're supposed to have reactive streams as an interoperability specification. You're supposed to be able to use multiple libraries. So the level of efficiency and the alignment between these libraries really matters. And finally, an example with our web client. So we have a server-side support for REST scenarios in M1 that you can try already. And we also have a web client that's fully reactive and also supports both Reactor and Arak Java. Now, we have reactive efforts across the Spring projects. There's already a Spring Boot reactive web starter. If you go on Start Spring.io and you choose Spring Boot 1.4, you can type reactive and you can get started in 5 minutes. Spring Security is also already on the path of experimenting with all this. Spring Data, there are already concrete results that you should check out the presentation once the videos are available. And Spring Cloud as well. I actually want to take a moment to talk a little bit about Spring Cloud Stream because I think this is an interesting example to highlight from a very different perspective. So we have web request processing, and you can see how a high concurrency of request processing we can really benefit from the non-blocking style processing. However, with Spring Cloud Stream, you have a slightly different scenario where you have constantly flowing data. So it's interesting to see and understand why is the reactive paradigm important and valid here as well. Now, for those of you who may not know, Spring Cloud Stream is a microservice message-driven framework. It allows you to connect microservices so they can communicate in event-driven style as an alternative to REST and HTTP. And it abstracts away the messaging middleware that's used to actually pass these messages. And it's extremely simple. You can see in this example, we're taking a message from an input channel, and then we're producing a message to an output channel. There are many more ways to do this. Spring Cloud Stream provides different ways. You can have multiple input channels. You can have no input channel, no output channel. You get the point of what is being done here. Now, what's interesting about this is, and why is the reactive paradigm important, is because, first of all, because it brings a functional style declarative API that you can use to declare operations, and not only on individual messages, and this is the second point, but also on the whole stream of messages. So, for example, if you wanted to take subsets of the incoming messages and then apply some operations to them, this is something called windowing, then you can do it like that. You've all heard of trending, right? So this is an example where we are trying to take all the incoming messages. Remember, this is a continuous flux of messages, once again. And we're selecting every 1 second, we want to pick the most trending words over the last 5 seconds. That's what this enables. First of all, it gives us a functional API. And second of all, it allows us to operate, and you can see here Flux in action. You can apply operations on subsets of the data as it flows through. Again, a very different scenario from web processing, but you can clearly see the benefits of using that. And for the rest of today and tomorrow, we still have a number of sessions on this topic. So please check those out and have a great show. Thank you.
Thank you.